All right. Hey, everybody. A lot of people are texting me, or I guess texting me, comments in Google Classroom about homework 1010. Kind of expected it. It's a little bit different. It's a little more application based. It's not just do this equation kind of thing. But it's also not hard. If you're struggling with it, it's because something's not clicking. It's not that you can't do it. I promise you, you can do this. And so I'm just going to do the key. And if you want, it's due today. If you want to just copy down my answers that I've done, listen to this video, get credit. There you go. That's how this class works. Like, you do the stuff, learn it, copy it, do what you got to do. Eventually, I'm going to test you on it. I'll get you a grade there. But that's what it is, right? So learn it. I care about you learning it. I care about you being able to do it. So here we go. First question, Model 1. Model 1 is a 3-drop, a 3-level, 1, 2, 3-level electron diagram. So I can be at the ground level, I can be at level 2, or I can be up at level 3. All right, so I've already kind of given you some info about the A drop and the B drop. Again, B is from 3 to 2, A is from 2 down to 1, and C is from 3 all the way down to 1. And I've given them the numbers. You didn't have the numbers. Numbers don't really matter. When we see this, we know the wavelength. We know the wavelength of A and B. A is 680 nanometers. B is 550 nanometers, and C is some unknown thing. So, number 1, determine the energy of a photon associated with transition A. I'm not sure where A went. Hopefully it was in your assignment. Maybe it wasn't, but you figured it out. A. Well, this is energy of a photon due to a drop. Well, that's going to be E equals hc over lambda, which is wavelength. E equals hc over wavelength, which is 1240, because remember h times c is 1240, divided by 680, gives me 1.82 electron volts. So I know that the drop A is 1.82 electron volts and has a, again, wavelength of 680 nanometers. Boom, that's it. Number 2, what's the energy of the B transition? Well, if the wavelength of B is 550, then it's going to be E equals hc over lambda, or hc over wavelength. And that's going to be 1240 divided by 550, or 2.25 electron volts. Right? A little bit more energy, and if you look at the diagram, you can see that B is a larger drop than A. So it's a higher energy. It lost more energy dropping that distance. All right. So then 3 says determine the energy of transition C. So what is the energy of the photon that leaves from C? Well, C is B and A. It's both drops. So it's just going to be A plus B. It's going to be 1.82 plus 2.25, or 4.07 electron volts. All right, so that energy drop is just the two together. This is quantum physics. This is quantized values. So if we know 2 of the values, then the third value is just add them up. 4, determine the wavelength of this photon. Well, I'm going to use the exact same equation. I'm going to use E equals hc over lambda. But I need to solve for wavelength. So I swap the E and the wavelength. This is a little trick. Talked about it in my other video. It's an algebra thing. You could have done the algebra of this, but I do that quick little swap. So now I know that wavelength equals hc over E for energy, which is 1240 over 4.07 electron volts. And when I do that math, I get 304 nanometers, 304 nanometer wavelength, which is pretty small. Well, next question gets to that. So remembering that the visible light is violet 400 to red at 700 is the wavelength for the photon in the visible spectrum. Well, no. It's 304 nanometers, which is smaller than 400 violet. It's actually in the ultraviolet range. We wouldn't see the light produced, or I guess I should say electromagnetic wave produced by transition C. I'm only going to see a spot at A and B. So ultraviolet. So then finally 6 is plot the spectrum. Create that those line spectrum for this atom. What would the emission spectrum look like? Well, I just need to draw a line. You're just going to plot lines at the spots. So first off, the 300 is outside the visible spectrum, so we wouldn't plot that one. And then the other 2, I plot a line at 550, and that would be green. and I plot a line. Ooh, let's go this way. I plot a line at 680, which would be red. Okay. All right. Model 2. So now I've given you the spectrum. So I've given you these lines, and I gave you the wavelength that goes with it. But I've given you each of the lines. And just say, hey, here's the drops that you see, A, B, C, and D. Which one goes with which one? Well, drop A is the biggest drop, producing the highest energy short wavelength wave. So that's going to be the violet that we see there. Drop B is a 1, 2, 3 drop. And so it's going to be a little bit less energetic. It's not 4, it's only 3. So that's going to be the next one, blue-violet. C is from, what is that? From 4 down to 2. So that's going to come away with even less energy. So that's going to be our blue-green wave, 486. And then D is only a single drop from 3 down to 2, which will give us a largest wavelength, which is actually the smallest energy, and that's our red one. So that's the last of the 4 waves there. So again, I said that here. A is 410, B is 434 nanometers, C is 486 nanometers, and D is 656 nanometers. All right. Model 3. This seemed to be the one that most people just, you know what, Mr. Egger, I'm done. I tap out. I'm out. I give up. See what this does here. All right. I think we can see the whole thing here. Model 3. Unknown element. All I've got are the different electron levels for this element, and they conveniently are nice even numbers with the exception of the 2.3. So on the diagram, I ask you to draw or indicate each of the transitions. So you could tell me, or you could draw a line, and there's 6 of them. So you could have a drop from the 1 down to the 2. I called that one A. You could drop from the 1, or negative 1, I should say, negative 1 down to the negative 2.3. That'd be B. I called that B. Or you could drop from 1 all the way down to negative 4. I called that C. All right, well, then we could drop from the negative 2 down to the negative 2.3. I called that D. You could drop from the 2, negative 2, all the way down to the negative 4. I called that E. And you could drop from the negative 2.3 all the way down to the negative 4. So those are all the possible drops that an electron could do when it drops down and releases a photon. Woo, woo, woo. Each of those would cause a different photon with a different amount of energy. So 9 says determine the energy for each of those photon drops, or each of those electron drops, which would release a photon. It's just addition and subtraction. I guess technically subtraction. Now they're negative numbers, so it's negative, negative, but whatever. A, we kind of did all the math out. So A is negative 2, final minus initial, right? Negative 2 minus where it started, negative 1. Negative 2 minus negative 1 gives me a negative 1 electron volt. So A is a negative 1 electron volt difference. That would be the energy of A, the first drop. B, negative 2.3 minus negative 1 is a negative 1.3 electron volt. C would be negative 3 electron volts. That's negative 4 minus the negative 1. D would be negative 0.3 electron volts. That's negative 2.3 minus negative 2. E, that was the one I said from 2 down to 4. So that would be negative 4 minus negative 2 is negative 2 electron volts difference. And F is negative 4 minus negative 2.3. And that's a negative 1.7 electron volt difference. All I'm doing is finding the difference between two numbers. What is the difference between the two levels that the electrons drop between? Cool. All right, 10. On the spectrum line below, plot the lines you'd expect to see. So you only need to plot the ones that would show up. I've got 6 different photons that shoot away, but only 3 of them will actually show up in the visible spectrum that I've given you here. Again, between 700 and 400. Now, I know one is below 700, but 700 is kind of an estimate. So I kind of said that on this. So we just look through it. So let's look at A. A, negative 1 electron volt. Nope, that's below the 1.7. That's in the infrared range, and we're not going to see it. B, negative 1.3 electron volts. Nope, that's below that 1.7 that's on the plot, so we wouldn't see it. That'd be infrared. C is -3 electron volts. That one definitely would show up. And it would show up in the violet, or right there below 400, so I call that violet. But again, just put a line there at the 3. Again, the colors come from 11. I'll hold off on the colors. And then D wouldn't show up. E, that's -2. Yep, that's on there. Put a line at -2. And then F, -1.7. Sure enough, that's on there at the end. So I put a line at 1.7. So then 11, you've seen the graph above and your knowledge of color numbers, and you can look back at the lab for these. What colors would they be? Well, this 1.7 is plotting a little bit below the 700, so I called that infrared / a little bit of red. The yellow is, or sorry, the 2 is plotting just below the 600, so that's in the yellow area. And then the 6, or the 3.0 is plotting just below the 400, so that would be a violet, indigo. Again, if you said blue or violet, I would have given you full credit for that. So just about what color would each of those things be based off of the number that it's near. Hopefully this helps. I know if nothing else, everybody should be able to finish the work. Again, give me comments. I'm standing by my phone. Well, not standing by my phone, but I have my phone on me ready to send you back a text message. And I send them back quick. You send a comment, I send you a voice. I do voice dictation with my phone to give you the answer. Sometimes I proofread them, sometimes I don't. So if they say something that's not exactly, that doesn't make much sense, that's why. Have a good one. Enjoy the Cosmos, and do the Cosmos quiz. See y'all.